In this section, we're going to discuss conjugated unsaturated systems. We're going to start by talking about allylic systems. An important component of allylic systems is the fact that they can do resonance. The allyl group itself has the following structure. It is a carbon attached to the carbon of a double-double bond. It is not one of the carbons of the double-double bond, but it is an adjacent carbon to the carbon-carbon double bond. We call this position directly adjacent to a carbon-carbon double bond the allylic position. Allyl group is in itself a common naming group. So for example, if we look here, we have an allyl attached to a bromine. So if we were to name this alkyl halide according to the common name, we would call this allyl, that's the name of the group, bromide. A carbon adjacent is called the allylic position, and it's given a special name because it has a special reactivity caused by its location adjacent to the pi bond. We're going to look at two types of allylic intermediates, and we're going to see how the fact that they are on allylic positions changes their properties somewhat. The first one we're going to look at is allylic free radicals, or allylic radicals. These are radicals that are on an allylic position on a carbon adjacent to a carbon-carbon double bond. One important feature of the allylic radical is that it is stabilized by resonance. When we do resonance with free radicals, it works a little bit different than the way that we push electrons when we have two electron species. In this case, you can see from these arrows, what happens is the free radical pulls one of the electrons out of the adjacent pi bond. This second line is really two dots, two electrons. So it pulls one of those pairs of electrons out, it makes a match with the original radical. That now creates two electrons in this space, which means that now we have a double bond here as opposed to in the original position. The remaining electron in the second bond of the double bond has to go somewhere, so it moves in the opposite direction out onto the other carbon of the double bond. The result of this electron movement then would look like this, where now the pi bond is between the right-hand two carbons, attached directly to what was originally the allylic carbon. And the radical is now actually on the far end of the three-carbon system. Remember that when we have resonance structures, the resulting species is more stable than it would otherwise be. An example of that, for example, would be here, where this radical would be a primary radical if there were not resonance. Primary radicals, we know, are here on our list of radical stability. Methyl radicals were the least stable. The primary radicals were more stable than that, but secondaries were even more stable, and tertiary were even more stable, radicals being stabilized by having additional carbon groups directly attached to the carbon of the free radical. We actually have a rough measure of the stability in the bond dissociation energy of the various carbon-hydrogen bonds that would make the radical. When we take a primary radical and we allow it to become allylic, the resonance stabilization lowers the bond dissociation energy by about 7 kilocalories, making it just about as stable as a tertiary radical by itself. Recall that secondary radicals are even more stable than primary radicals. In that case, a secondary allylic radical, which would have carbon group also attached on the other side away from the pi bond, are even more stable. The bond dissociation energy is 87, and in fact, it would be preferable to form a secondary allylic radical to even forming a tertiary radical that was not allylic. So this then becomes our new table of radical stability, adding in these two new structural possibilities. Allylic carbocations are also resonance stabilized. We've seen this resonance before. A carbocation represents an empty space, a carbon with an incomplete octet. So in this resonance, to create the resonance structure, we imagine the pair of electrons in the pi bond moving toward the empty space, shifting from between the left two carbons over to being between the right-hand two carbons, creating a new double bond. As that pair of electrons moves away from the far left carbon here, it creates an empty space, which then becomes the carbocation. Notice that the arrows have a different shape because we're moving the entire double bond, both electrons, so we use a double-headed arrow. We see that allylic carbocations are also more stable than tertiary carbocations, although primary allylics are probably very close to tertiaries, similar to what we saw with free radicals. This stability of the allylic radical allows us to do another type of regioselectivity with bromination, which you'll recall bromination was selective. We call this allylic bromination. We can selectively put bromines at allylic positions in a molecule. The observed reaction looks like this. So here would be a molecule that would have a pi bond and hydrogens on allylic carbons. To do this, we're going to use a reagent that is abbreviated NBS. And in fact, most organic chemists just use that abbreviation to name it. NBS stands for something that I'll show you below. We still use heat or light because it is still a free radical reaction that requires activation. And at the end of the reaction, we will have selectively replaced an allylic hydrogen. Now, we saw in the last section that we could just use Br2 to put bromines into a molecule using free radical bromination. Why don't we just use bromine here? Why instead are we using this reagent, NBS? Well, NBS stands for N-bromosuccinimide, and it has this structure. You're never required to write this structure. You can just write NBS. But what we have is a succinic acid, which is a 4-carbon dicarboxylic acid, in a cyclic amide ring with 2 amide bonds to the same nitrogen. When you have 2 amide bonds to the same nitrogen, instead of being called an amide with an A, it's called an imide with an I. Then we have a bromine also attached to the nitrogen of the diamide. So that's the N-bromo part. This substance very slowly decomposes to give us a very low concentration of Br2. So technically we will be using Br2 in this reaction. However, the problem is that if we just put in a large concentration of bromine, Br2, we would see that the bromine would rapidly react directly with the alkene from a reaction that we learned in chapter 8. Alkene plus Br2, we lose the double bond and we add bromine to each side. It turns out that this bromination reaction has a complex mechanism in nonpolar solvents, where it actually requires two molecules of Br2 to collide together at the same time that you collide with the alkene. So it's actually has an order of 2. It's bimolecular in bromine. By putting in NBS instead of Br2, we create such a small concentration of bromine at any given time that it's really unlikely that two bromine molecules would find each other to collide, and so therefore we don't have reaction directly with the alkene. When we do allylic bromination on molecules that are not symmetric with regard to the double bond, we have, it turns out, multiple regioisomers possible. And we generally see all of the possible regioisomers being formed in the reaction. Here's an example. If you look, here is our original double bond at the end of this 4-carbon chain. On carbon 3, we have an additional methyl group. When we use NBS and ultraviolet light, we selectively replace the allylic hydrogen right here. So we get this product. But we also get a product where the double bond has shifted over toward where the allylic hydrogen was originally, and the bromine is now on the far end of the allylic system. To see why this occurs, we can look at the mechanism of this reaction. So in this reaction, looking only at the propagation steps, in the first propagation step, a bromine radical would remove the allylic hydrogen selectively because that would have the lowest carbon-hydrogen bond association energy. When it removes the allylic hydrogen, the other electron from the carbon-hydrogen bond would move onto the carbon, and we would get this allylic radical. But as we mentioned, the allylic radical has resonance. So we get this intermediate, but we also get this as a way of looking at the intermediate. The real intermediate is a mixture of these two structures, but these represent sort of extreme views of the individual structures. From our point of view, what we can see is that we have free radical character on this carbon, but we also have free radical character on this carbon. In general, when we have a reactive intermediate, by which I mean a carbocation, a radical, or a carbanion, and that intermediate has resonance structures, we will expect to see some amount of product formed from all of the resonance structures. Although I should point out that it will not be the case that we will get equal amounts formed. There will often be other circumstances that will drive us to prefer still fewer than all of the possible products. In this case, however, there is no other circumstance. And so in the second step of the propagation, the carbon radical grabs a bromine atom, forming a molecule of product and another bromine radical, which can go back and continue the free radical chain reaction. If we imagine that the radical is centered on this carbon, that would put the bromine here on the original carbon hydrogen. But if we look at the resonance structure, the radical is centered on a different carbon, so if it grabs it from that point, the bromine would be in a different location.